Thank you for being here. I know it's a post-prandial afternoon, but hopefully I'll get you guys a little bit excited. And thanks to ARM for making this fantastic meeting in a very fantastic location. We're located in San Diego, California, so we're in the neighborhood. We're all about advanced reparative medicine. We're medically repairing damaged organs and tissues. So, next slide. Little forward-looking statement slide. Right, so some of the things about Angiocrine that you've probably never heard of, because we've been in a kind of a stealth mode thus far. We have a new class of therapeutics that we're developing where we medically repair damaged organs and tissues. They are allogeneic, human-engineered endothelial cells, trademarked E-cells. We have 2 E-cell clinical products in the pipeline. One is entering late stage, phase 3, to repair multiple organs. And the other in early mid-stage. This is more of a local treatment rather than systemic, and that is to repair local tissue damage. We have a growing research pipeline that is organically generated, and we have a potential expedited approval path under US FDA RMAT and orphan drug designation. So a little bit about the science of repairing organs and tissues, and we're going a very unique approach. I'm going to talk a little bit about vascular stem cell niches. So you may or may not have known that you have the capacity within you to repair organs. These are called vascular stem cell niches, and picture something like a very microscopic bird's nest. And within the nest are these little eggs, and there are your adult stem cells, or some people call them organ-specific progenitors. Now, surrounding them is the nest made out of endothelial cells. Endothelial cells are lining of the vessels, and they produce angiocrine factors. Angiocrine factors, think of it as instructional code, like a complicated computer code, and it's telling the stem cells, you guys stay asleep. Okay, we have a problem here. You guys wake up. Some of you divide and become mature cells, and others, you stay stem. And our vascular stem cell niches in our body have different activities. So some are very, very active. So in the bone marrow, you produce about 1 billion cells a day. In the gut, you actually reline your mucosal lining on pretty much daily basis. Everybody knows that if you get injured, you have musculoskeletal injury, you could kind of rebuild your muscles. So those are readily inducible niches. Liver is known to be regenerative, lung somewhat so. And then there are the quiescent ones like heart and the CNS, but they could be woken up given the right environment. Now, a little bit more about these endothelial-derived angiocrine factors. They direct the adult stem cells. They're very complex. It's really the mixture, which is the magic. Each organ determines what kind of angiocrine mixture that they would want. Many organs have very specialized organ-specific niche endothelial cells. There's a constitutive mixture. That's to maintain your organs. And there's the reparative mixture when you have injuries or diseases. And physically, the endothelial cells are co-located with the adult stem cells as we pictured as a bird's nest. So the dynamic complexity of the angiocrine factors makes it almost impossible to constantly create a cocktail of recombinant factors. And that's why we came to think of, well, why not use the endothelial cells themselves as a therapy? The problem with our vascular stem cell niches is that if you're middle-aged and older, your capacity to recover start diminishing. And everybody would know that if a young child breaks a bone, they heal pretty much all the time quickly. But your aged grandparents have a high risk for malunion and fracture or even get infected and then never the same again. That's your aging vascular stem cell niches in that case in your bone and your muscles. There are other diseases. There's plenty of diseases that actually affect your vascular stem cell niches. So we talked about age-related degenerative changes. Cytotoxic treatments wipe out diffusively your vascular niches in different parts of your organs. autoimmune disease attacked your microvasculature, then you have your classic microvascular and ischemic diseases. So plenty of diseases to address. This all started happening about 20 years ago when somebody thought, actually a very intelligent professor at Oregon and another one at Duke, thought endothelial cells, let's use this as a therapy. And their rationale was endothelial cells, and especially blood stem cells, have a common origin. So maybe the endothelial cells, some of them, could become stem cells. So they did an animal model of total body irradiation, and without giving blood stem cells, they just gave endothelial cells, and voila, the mice all survived. Magic, right? To their disappointment, they realized that the endothelial cells don't become blood stem cells. What happened was that the endothelial cells rescued the very few remaining blood stem cells in the animals and repaired all these organs, and that's how the animal survived. So that started the whole history of the idea of giving endothelial cells as a cell therapy. The problem is, though, primary endothelial cells, they have very, very variable reparative potency. And when the experiment started, they started using microvascular brain endothelial cells. That's, can't make that really as a therapy. They also don't maintain being an endothelial cell. When you put them in culture, it's something called endo-empty transition, so they become mesenchymal stem cells. They're just not scalable. So the whole field kind of stopped after 10 years, but then we came about and said, well, if we could engineer endothelial cells and overcome these problems, maybe we could make this a fantastic new way of repairing organs and tissues. And exactly that's what we came up with. It took about 10 years of hard work. We did genetic engineering. What we do is we take HUVECs, which are neonatal, very, very abundant supply. It's actually medical waste. So HUVECs are human umbilical vein endothelial cells. They're very plastic, and we actually harvest them in a proprietary manner under FDA regulation. We engineer them using transductions of at least one gene called E4. It's an adenoviral gene. It's a pro-survival gene, and others. And by doing that, we now have something called E cells. And they are engineered human endothelial cells. They're robust. They have very robust potency. They're allogenic. We could give them off the shelf. They're purifiable. And as importantly, they're scalable to be a commercial product. So how does it work? The E cells really don't do anything until they enter the body and encounter disease states or injury. So they're usually a mixture of cytokines of some kind. And when they do that, they know through evolution to start expressing reparative mixtures of angiocrine factors. And that does two things. It provides angiocrine factors, remember the instructional cues, for the adult stem cells in your organs to wake up and start doing their thing, which is repairing your own organ. The other thing it does is it actually rehabilitates the microvasculature, which is usually the component that's damaged in your vascular stem cell niche. And by doing so, over the 3 to 5 days time period, it kickstarts and revives your natural process. So this isn't anything stimulatory or abnormal. It's really just to revive the natural ability you have to repair yourself. We've done a lot of different animal models, and based on this, we have created 2 clinical programs. The first one, I mentioned before that if you have myeloablative chemotherapy, that means you wipe out your bone marrow. You have this heavy-duty, high-dose chemotherapy. Not only do you get rid of cancer stem cells in your bone marrow, and it's one of the very few things that are curative, but you also destroy your ability to recover. And as you could imagine, remember, we're relining our mucosal lining on a daily basis. If that stops, what happens? You get mucosal breakdown. Then what happens? Well, you get very painful ulcers, you're very sick, but also you have a lot of bacteria in your gut. normal gut flora. That starts spilling out into your blood circulation, so now you are in a big high risk for sepsis. And you're also pancytopenic, meaning you don't have the blood cells to fight off the infection. Remember, your bone marrow lining is also in a state of disrepair. So you have a big problem. So much so that this has been recognized by the FDA through the RMAT designation. So we have presented this study in several meetings, ASH last year and in a transplantation meeting, and we're going to again present an oral presentation at this year's coming ASH. It was our phase 2 study where we compared, it was dose escalation study compared to a retrospective control cohort. So these patients are lymphoma patients. They go through 1 week of high-dose chemotherapy. Everything gets wiped out. They have standard of care prophylaxis like anti-infectives, growth factors. They get everything thrown into them. And despite that, about 40 to 50% of them get very severe complications. And we're looking at severe pan mucositis, so from oral all the way down to your anus. We're looking at hematopoietic recovery. We're looking at neutropenic fever, which is fever in a state of pancytopenia. That's a medical oncology emergency. And we're looking at incidence of severe infections. As you can see on your left, this being a non-confidential presentation, we could only share with you the top line, but it's pretty impressive that we had about 40-50% of severe pan-alimentary mucositis incidence in the retrospective control cohort compared to all dose 9% reduction, so very significant reduction. And in our highest dose, 20 million per kilogram, there was 0% of severe oral GI toxicities. We were very blessed to have great partners with us, City of Hope, Memorial Sloan Kettering, MD Anderson, so forth. And this study was also co-funded by CIRM, California Institute of Regenerative Medicine. Quickly, I got 2.5 minutes left. We're not just about transplant, stem cell transplant and high-dose chemotherapy, but we have a second clinical product that's looking at local repair of damaged tissues that are age-related. We have a program in perianal fistula that's being conducted by Cornell, and we have an early clinical proof of concept in that study. And as well, we're doing a tendon repair study. We're starting with a rotator cuff. So rotator cuff tear is, again, a condition of middle age and older. And what we're doing is we're actually providing the cells almost like a living glue to be placed between the tendon and the bone as they put the sutures in. And this is being conducted by Professor Scott Rodio at Hospital for Special Surgery, also in New York, and we have, again, an early clinical POC for that as well. And finally, we're cooking up more E cells, or what we call the next generation E cells. So what's in the clinic, we nicknamed as universal E cells because they tend to work in bone marrow, GI, soft tissue. But some of the other organs like lung, heart, they need more engineering, more specificity for that organ. So we're cooking up and have made already pulmonary, hepatic, thymic, immunological E cell, cardiac, and angiogenic E cell. So in summary, we're very excited to continue our clinical work as well as our research work in achieving our dream of repairing organs and tissues through medical means. And I appreciate your attention very much. Thank you.